Okay, so we've got our formula equation written, but it's not balanced yet. So we need to go back and balance our total equation. Okay, and so I think to do that, let's see. I can see automatically I'm going to need 2 nitrates, right? So I'm going to go 2 here. Then that balances sodium. So I look over at sodium. Sodium's already at a 2. So that seems good. Okay, what other things do we need to balance? What'd you say? Nothing. Okay, sorry, I thought you said nitrate. I'm like, we just did that. Okay. So we have 1 barium on each side, 2 nitrates on each side, 2 sodiums on each side, and 1 sulfate on each side. We good with the balancing part? Okay, so formula equation is done. Okay? Now we move on to the complete ionic equation. This is step 2, right? The second level. We put all of our ions as ions. So this is a complete ionic equation coming next. Okay? So I'm going to go a little bit faster here. We're going to split these up. So if barium and nitrate get into water and split up, how many barium atoms do I have? Just on the reactant side. Just 1. So barium and its charge is +2, and we know it's aqueous, right? Because it's dissolved in water. This ion is dissolved. Okay, how many nitrate ions do I have? I have 2 right here. So I say 2 NO3 minus 1. It's also aqueous. Okay, so we need to do that for all of our compounds for all of our compounds, okay? Next, how many sodium ions do I have? 2. So 2 Na plus 1, which I know is aqueous. And how many sulfates? Just 1 right there, minus 2. And it is aqueous as well. Okay, then I say, okay, that's all my reactants. I draw my arrow. My products, I have 2 sodium ions, 2 Na plus 1, which is aqueous from here, plus 2 NO3 minus. Sorry, I forgot my 2. 2 NO3 minus, which is aqueous. Plus, I have a barium sulfate molecule that's a solid. So do I split that up into ions? No. Okay, so I keep that BaSO4, and that's a solid. Okay, so that's your complete ionic equation. Yeah?
Okay, so you don't split that up because it stays...
Because it's their precipitate. That's what your solid is. Yeah, so in our final, this would be after our reaction takes place. This is what we have left in our beaker, right? We have 2 moles of sodium ions, 2 moles of nitrate ions, and then this solid. Right? So after our reaction has taken place, all of these ions have mixed. I've got 2 moles of sodium, 2 moles of nitrate, and this 1 mole of barium sulfate. Solid. Okay?
And why doesn't that split?
It doesn't split because we know it's not aqueous. It's not dissolvable in water. So once the barium and the sulfate molecules bond, they're no longer dissolved, they're no longer soluble in water, so they're going to stay as a solid. They don't dissolve. We're talking about what ions are present. And so barium is no longer an ion. It's paired with sulfate, which makes it a compound now. Yeah?
Do we have to put the charges in?
Since it's an ionic equation, you have to have the charges with it. Yeah, good question. Okay, so Jenny asked whether we have to put the charges, and we do because it's an ionic equation. Yeah, good question. Not with this because that's our compound. It's no longer an ion. It's put together into this new substance now. Okay, questions about that? Now the net ionic equation is only looking at the ions that are involved, right? We leave out what we call the spectator ions. Okay, in this case, spectator ions are sodium and nitrate, right? They don't actually happen, they don't do anything in the reaction. We start with 2 nitrates on this side, we end up with 2 nitrates on this side. We start with 2 sodiums here, we end up with 2 sodiums here. They didn't do anything in the reaction. They were just there. Okay? They didn't do anything. They spectated. Okay? So our net ionic equation just deals with the ions that were involved, which we know to be barium and sulfate, which yielded barium sulfate. Right? So barium started at barium plus 2, which was aqueous, plus sulfate, SO4 minus 2, which was aqueous, yields BaSO4, which was a solid. This reaction, if you did it right, this reaction should automatically balance. There should be no need to balance that reaction. As long as you did it correctly here, then transferred the number and the moles of ions correctly here, everything should balance right, which it does, right? 1 barium plus 1 sulfate yields barium sulfate. Sodium and nitrate did nothing. They were not productive in this reaction. They just watched. Okay?
Would we ever have like a formula, I guess, that has multiple solids?
Okay, so we want to find out what mass of lead sulfate is formed when we mix 1.25 liters of this solution and 2 liters of this solution. So this is practical lab application stuff, right? We have this concentration of, 1.25 liters of this solution and 2 liters of this solution. We're going to mix it and we're going to see how much comes out, right? That's what stoichiometry is putting a quantity to our chemical reactions. Okay, so we're going to start with our formula equation. I'm going to tell you your book puts a lot more steps into problems than needed. So if you are looking through your textbook and you're trying to look at their examples, they do too much work. Okay, I was trying to look through your book to refresh these examples and wow, okay, like they just do too much. So just keep that in mind when you're looking through your textbook. If it's confusing you, like, it's okay. It confused me too, okay? So your book, I think, puts too many words for simple problems. So I'm going to walk you through what I think is the easiest way to get to where we need to be, okay? Your book will tell you that you need the net ionic equation here, and I disagree. So we're going to stick with the formula equation, and we're just going to do regular stoichiometry, and it works the same. Okay, so I'm just telling you that if you like to refer to your textbook, because I think they do too much work, okay? All right, so let's go formula equation here. We know that lead sulfate is a product, so I'm not going to worry about that yet. I'm going to look at what my reactants are, and they are lead 2 nitrate and sodium sulfate. Okay, so lead 2 nitrate would be PbNO3 2. Right? Lead is a +2, nitrate is a -1, so I put those together, I get PbNO3 2. Okay, my second reactant is sodium sulfate, Na2SO4. Okay, please stop me if I'm going too fast putting together chemical compounds, but I feel like we're comfortable enough with those that we can move at that pace. Okay, if I need to do one, let me know. Possible products I know should be lead 2 sulfate, right? PbSO4. Right, that's my first combination. My second combination is NaNO3. Okay, next step is balancing. Any questions about the compounds themselves? Yeah, Ethan.
Did you put aqueous and salt?
Yeah, we do need to put aqueous. I'm going to go through and balance it first, and then we'll walk through. I told you last time we'd do it individually, and then I forgot. Okay. Yeah, so we are going to go through and figure out which ones are aqueous and not. Let's balance first, and then we'll go back and do that. Good question. Thank you. If we need to balance, I see right away I need 2 nitrates, so I'm going to put a 2 there. That leaves me 2 sodiums, which is what I need. So is that finished balancing? Okay, great. Now let's go back and look at our aqueous and which is our precipitate. Okay, lead nitrate, what do we know about all nitrates? All aqueous, okay? So nitrates, if we know all nitrates are aqueous, I'm just going to put an AQ on both sides since I've got a nitrate on both sides, right? Sodium sulfate, sulfates are all soluble except for strontium, barium, mercury, and lead. So that means sodium sulfate does not fall into that category. So it gets an AQ. But lead sulfate does fall into the exception category, which means that's our solid. Okay, which is good because we want to find what's the mass of that. So that should have been a clue for you there. That was your solid. Okay? Any questions on how we got which one was aqueous or solids? Okay, sulfate's all soluble except for those 4. And lead falls into that. Okay, great. Now we need to find out, we have 2 starting amounts of reactant. We have 2 starting amounts of reactant. And what do we know about all stoichiometry problems if we have 2 starting amounts of reactants? What do we need to find? The limiting reactant, right? If we get 2 starting amounts, we've got to find out which of these is limiting. Okay? So luckily for solution stoichiometry, it's a little bit easier because you're going to use your molarity equation to find moles for each of these. Okay? So let's look at my first one. I have, let me get rid of this junk up here. My first reactant, I have 1.25 liters of 0.05 molar of lead nitrate. So I'm going to use my molarity equation, molarity equals moles over liters, to find out how many moles of that reactant I have. Right? In our past problems, we started with grams, and we had to do a T-chart to find out how many moles. Okay? But we can just look at number of moles here to find which one is limiting. Okay? All right, so if I wanted to find the number of moles of that, I would say 0.05 molar equals moles over 1.25 liters. Right? And if I want to find moles in that scenario, what do? I multiply 1.25 times 0.05, and I get 0.0625 moles of PbNO3 2. Okay. I do the same thing for my second reactant. 2 liters of 0.025 molar. So if I need to find my limiting reactant, I need to do, I need to look at how much of each of these products, how much of my product can I make from each of these starting amounts, right? That's what your limiting reactant is how much of my product can I make based on each of these starting amounts. And so I'm going to take my starting amounts of moles of each of those, and I'm going to convert to moles of my product to see which is my limiting reactant, right? Because we know our starting amounts of each now in moles, and now I'm going to convert to my product to see which of these is limiting my reaction, okay? So I want to go from moles of lead nitrate, and I don't have room there, I'm running out of room, to moles of my other product, lead, sulfate, PbSO4, okay? Okay, and how do I get these numbers? Where do they come from? That's my mole ratio step. Where do they come from? Directly from my equation, and they are 1 to 1. So the math behind this is really easy. So that's saying if I have 0.0625 moles of lead nitrate, I could make 0.0625 moles of lead sulfate. Okay? That happens because it's a 1-to-1 ratio. So you don't really have to do the math with it, but I'm just proving that to you. Okay? Does everyone see where I'm at right now? Okay, I found my starting amounts of each, and I converted to see how much of my product I could make. I'm going to do the same for my other reactant, which is NaOH. Na2SO4. Moles of PbSO4. I get these numbers, again, directly from my balanced reaction, and they are 1-to-1 again. So that means if I have 0.05 moles of sodium sulfate, I can make 0.05 moles of lead sulfate. So which of those is my limiting reactant? Is lead nitrate or sodium sulfate my limiting reactant? Sodium sulfate. Okay, so that means I can only make a maximum of 0.05 moles of lead sulfate. Okay, this is the product I'm looking for. That's the maximum amount that I can make. But I want to know mass. So how do I finish my problem here? Convert to grams. So 0.05 moles of PbSO4, 1 mole, and then our molar mass goes up top. You could have done that in one T-chart since we were looking for grams. I was just kind of running out of room there. Yeah, you could have done it in one swoop. That would have been fine. Okay. Molar mass for lead sulfate, I had it at 303.2. And my total amount of lead sulfate formed, I had at about 15.16 grams. Write it up here at the top. 15.16 grams. Okay, it says find the mass of NaCl that must be added to this silver nitrate solution to precipitate the max amount of AgCl. So let's talk through what that means. We're going to have reactants of silver nitrate and salt, right, sodium chloride, that yield silver chloride and something else, right? We'll figure that out in a second. But we want to find out how much salt has to be added to that solution of silver nitrate in order to give us the maximum amount of our precipitate. Okay, so we know in this case that silver nitrate's our limiting reactant because we want to find out how much salt we have to add in to get all the silver chloride we want. Okay, so let's write out our formula equation. What mass of NaCl, that's got to be one of our reactants. NaCl has to add to our silver nitrate. So AgNO3. All of these are ones, so that makes our problem really easy. Okay? We know silver chloride is our precipitate because it says it in the problem. We're going to prove that here in just a second. And then our final product would be NaNO3. Okay, so let's go through and check for solubility on each of these. NaCl, we think soluble or insoluble? It is soluble. Because chloride, all chloride ions are soluble except for silver, mercury, lead, so sodium doesn't fall into one of those exceptions. Okay, so we're going to put in this salt crystals and they're going to dissolve. You know what I'm saying? We're mixing it into that solution. We're adding it as a solid, but it's going to ionize in solution. Yeah, good question. Good question. Okay, so as soon as we put it in the water, it's going to dissolve and ionize. Good question, though. All nitrates we know are aqueous, which means this is aqueous as well. Okay, so we know silver chloride is our precipitate, and it matches on our solubility chart. Okay? Is it balanced already? Yes, they're all ones, so really easy to balance. So we want to find out the mass of sodium chloride that has to be added to this solution. So our first step is we got to know how many moles of silver nitrate are in there. We have to find out how many moles of silver nitrate because we can't use liters or molarity in stoichiometry T-charts at all, right? We got to have moles. So that's our first step. is we take our 0.10 molar solution, we find out how many moles of AgNO3 are in that 1.5 liters. Okay, so that gave us 0.15 moles of AgNO3. Okay? So from there, we can do a really simple stoichiometry problem. We want to go from moles of silver nitrate, and we want to find out how much in grams of salt, or NaCl, has to be put in to use up all 0.15 moles of silver nitrate. I can't talk today. Okay? We've got to find out how many grams of salt go in to react with all 0.15 moles of that. So we do a stoichiometry to problem to go from 0.15 moles, and we want to find out how many grams of salt will it take to use up all 0.15 of those moles. Okay? So my mole rate, or my stoichiometry goes moles of silver nitrate to moles of salt, right? Then moles of salt to grams of salt. And that's it. Okay, so moles of AgNO3 to moles of salt. Moles of NaCl to grams of NaCl. So where do these values come here in our mole ratio? Yep, from our balanced formula. It's a 1-to-1 ratio. So we know that if we need, or if we have 0.15 moles of silver nitrate, okay, let's just stop and think for just a second. In our regular reaction, we say, in order to form these products, we need 1 mole of this plus 1 mole of this. Right? In order to form our products, we need 1 mole of each. Now we're just scaling it down. We have 0.15 moles of this, which means we need 0.15 moles of this. And so we're just going to have that in grams now. Right? That's what this step tells us. Then we convert from moles of sodium chloride to grams. So 1 mole equals 58.5 grams. And multiply across the whole top, divide by the whole 8.76 grams of NaCl. Sure. It's just a rounding thing. Yeah, it's fine. If you're in the ballpark, 8.7 something, that's just great. Yeah?
I'm like still confused how you know what to do for each.
Okay, so because we want to find out the mass of sodium chloride, and that's one of our reactants, we're taking what we know. That's always what we start our T-charts with, what we know. So we converted that to moles to find out how much silver nitrate we started with, and we want to find out how many grams of salt have to be used up in order to get our products. So it says the max amount. Don't let that confuse you. That's just saying we want to get as much product as we can, so we need to put in enough salt to react with this. Okay, and so we're trying to find out what is that magic number of salt that will use up all of my sodium nitrate in order to form my product. Okay, does that kind of make sense? So you really have to search through the words and figure out what your stoichiometry is going to look like. Because I think it's really tempting to try to solve for your product, which we really don't need to know in this case, right? They didn't ask us for what is our max amount. It just asks us, in order to get to our max amount of product, what do we got to put in? Okay? So you have to like kind of find your way through the problem a little bit. Yeah.
For labeling them for.
Do you want to do it together, or do you want to do it on your own?
We go through it together.
Well, you want to go through the start of it together?
No, like at the end.
At the end, yes. You do it, get through as much as you can. I'll give you like a 10-minute head start, and then I'll start kind of writing some things on the board if you're stuck. Okay?